Most astronomers and theoretical physicists endorse the idea that our universe started with the Big Bang. However, problems with dark matter, dark energy, and cosmic expansion have some astronomers rethinking what we know about the early universe. Our universe appears to be expanding and cooling, having originated some 13.8 billion years ago in a hot Big Bang. However, it's plausible that what we see from inside our universe is simply the result of being inside a black hole. This is one of the most fascinating and yet least discussed possibilities in modern physics. Several scientists are now considering this outlandish idea by trying to connect the singularity in the black hole with the singularity in the Big Bang. It's completely baffling, but it is grounded in sound mathematics. While it may sound strange, it could actually be the best explanation of how the universe began, and what we observe today. Near the time of the Big Bang, entropy was very, very low, and it's been increasing for the past 13.8 billion years. The question is, why did the universe begin in such an ordered state?
Many physicists say this is the biggest question in physics, because the universe tends to disorder. That's the way it works. Everything gets more and more disordered. But so the Big Bang was a uniquely highly ordered, bizarrely, very strangely highly ordered thing. This is why the universe could have gone in many directions. You have to hear the Big Bang is a quantum fluctuation. There you go. It just fluctuated and it came into existence in this highly ordered state. It's been getting more disordered ever since. But disorder, the measure of disorder, is a measure of the probability that you will spontaneously create it. So if you're very ordered, it's very unlikely you'll create it. If you're less ordered, it gets more and more and more likely you'll do it. And that's why things get more disordered. So the universe today is less ordered than it was then. So it's far more likely that it would fluctuate into existence now than it would fluctuate into existence then. Because it's less ordered now, so it's more likely. So that means that the whole universe, with us in it, having this conversation, and everything we can see, is more likely that would fluctuate into existence than it is that the Big Bang fluctuated into existence. And it's clearly true, because it was very highly ordered then, and it's less ordered now. So you're faced with this massive problem that if you want to say it's a quantum fluctuation, it's overwhelmingly more likely, and I mean ridiculously, billions and billions and trillions of times more likely.
Black holes are perhaps the most extraordinary and intellectually challenging naturally occurring objects found anywhere in the universe. Some of the black holes observed today are many billions of times more massive than our Sun. Delving into the mysteries of our universe, Professor Brian Cox explains how they are formed, why they are essential components of every galaxy, including our own, and what secrets they still hold, waiting to be discovered.
So I talk about cosmology, what we call the large-scale structure of the universe, so the galaxies and how they formed, how the universe has evolved since the Big Bang. But also black holes. And black holes, and they're really evocative things. I think everyone's heard of these strange things, these totally collapsed stars, from which nothing apparently can escape. But in the past few years, past few decades really, beginning work that Stephen Hawking really began back in the 1970s and many others, we've begun to suspect there's a lot more to them. And they've started forcing us to reassess our understanding of what space and time are. And that's a really weird sentence. You might think, well, space is the arena in which we live and time just ticks, but it really isn't. It looks like, from studying these things, there are building blocks of space and building blocks of time. And so black holes, they're kind of a metaphor in a way, that by studying them, we're beginning to get a deep picture of what our reality actually is. That's a remarkable idea, but it's a beautiful idea that runs through all of science. But it's just a region of space from which even light can't escape. So Stephen Hawking, back in the 70s, calculated that black holes, they glow in the sky, like coals in the sky, and they radiate. And so over time, they lose energy and mass and ultimately disappear over huge timescales. And that's so important. This was the key in trying to understand what happens to the stuff that fell in. When you thought these things existed forever, then you think, well, it's okay, it gets locked up inside, it can never get out, we don't care. But the thing evaporates away, one day it will be gone. So then suddenly you have to be faced with this question, what happened to everything then? If I throw a book into a black hole, is it somehow possible in the far future, if you collect all this so-called Hawking radiation that comes off, is it possible to reconstruct the information in the book? That's been a question, simple question, that's driven this tremendous amount of research for 50 years. And it was pretty much solved in 2019, actually, in 2020. Well, the statement is everything comes out again, all the information comes out. So everything that fell in principle, in the far future, you could reconstruct the information of everything that fell in.
If you fall into a black hole, your body could be subjected to a process called spaghettification. So if we are inside a black hole, how is it that we are not getting twisted, torn apart, or spaghettified? Dr. James Beecham is a particle physicist at CERN. He searches for answers to the biggest open questions of physics and explores this phenomenon thoroughly.
To make a black hole out of the Earth, you need to pack the entire thing into a volume about the size of a blueberry. Most black holes we know of course, are much larger than this, with masses that are billions, tens of billions of times that of the sun, and with volumes that will encompass our entire solar system. What about the observable universe? We know that the universe is expanding, but expanding into what? Nothing. Space itself is expanding. Because of the particular way that the universe expanded right at its birth, we also know that there are parts of the universe that are currently unobservable to us. They are outside of the so-called observable universe. So there are parts of the universe that are so far away that we can't see them. So the observable universe is defined as this sphere that's around you that's composed of all the stuff that has had a chance to send a light signal that you could receive. But beyond that, we have no idea how big the entire universe is. So the observable universe right now is 93 billion light years in diameter. But the entire universe, we have no clue. It could be infinite, in fact. It could be something smaller. We don't know. If you wanted to make a black hole out of the entire observable universe, you need to pack it into a sphere that's about a little larger than the current observable universe. Do we live inside an enormous black hole? It turns out that as long as the black hole is large enough, you would be okay. It would still be a one-way trip. Once you cross this event horizon, there's no way for you to go back out. But it's entirely possible that our observable universe right now exists on the interior of an enormous black hole. Black holes are more than astrophysical oddities. And this event horizon becomes a barrier, a border, this thing that's always in the distance that you can never reach. No matter how quickly you travel, you'll never be able to get to that thing. We know that black holes eat things and grow. So this horizon, think about what it means to be inside of a black hole. You'd have this point of space, this region of space that you could never get to, and it's always receding from you, a horizon. But think about what it then means for you right now on Earth. If you look out into space, there is a horizon very, very far out, away, beyond which we cannot see, but we know there's stuff there, but we can never possibly see, and no matter how quickly you travel, you'd never be able to get to it. That's remarkably similar to what you would experience on the inside of a black hole. It turns out that the mathematics of the interior of a black hole is almost identical to the mathematics of the exterior of the black hole. This is actually what is going on. Mathematically, it makes sense as well.
While the idea that we live inside a black hole sounds fascinating, scientists need experimental evidence. So how can we test the universe inside a black hole idea? Perhaps there is a way to indirectly observe whether we live inside a black hole. But first, we need to learn how they are created. How does the universe make them? In order to understand singularities, we need to combine general relativity and quantum mechanics. We are fascinated by black holes because they could help us answer one of the biggest open questions, long-standing questions in physics, and this is the question as to whether gravity and quantum mechanics have anything to do with each other. Scientists continue their quest to try and combine these two theories, hoping for a more fundamental theory of the universe. Thanks for watching. Did you like this video? Then show your support by subscribing, ringing the bell, and enabling notifications to never miss videos like this.